So good morning. I'm going to be talking about programming, but it's not going to be one of those technical talks. It's more about the history of programming, the evolution of computers, and what makes our programming languages distinct. I personally like to have a bit of background knowledge when it comes to things I'm working with. So, I had a lot of fun doing the research for this talk. And I hope you guys find it interesting too. So we're going to get straight into it. So programming dates back around 850 when the Banu Musa brothers published their book called the Book of Ingenious Devices. This book mainly consisted of diagrams of about 100 odd machines, which they called automata. Basically automatic machines and devices that would perform functions based on pre-written instructions. But there was one machine in this book that stood out, and that was the automatic flute. The reason why the automatic flute stood out so much was because it was programmable. This flute produced sound using steam, and it had 1 and 2 wave valves that could be changed. And many believe that this is the first instance of someone actually programming a machine. Then we fast forward a little bit, about 1,000 years, and we have this guy named Joseph Marie Jacquard, who creates the Jacquard loom card system. So a loom is basically a device that weaves textiles into like patterns and materials, and this system allowed them to automate the process. So how it would work is a series of cards would be fed into the loom, and if there was a hole on the card, the needle would rise, and if there was no hole, the needle would stay down. And then this shuttle would travel across the loom, creating a pattern in the fabric. And then around the same time, we had the automatic piano players. This kind of operates in the same manner, where in a sense, it used early forms of punch cards. Moving on to the 1830s, we're coming up to some familiar names, and that's Charles Babbage and Ada Lovelace. So Charles Babbage developed the device called the Analytic engine. This basically was a mechanical computer which also used punch cards. The computer had things such as sequential control, branching, looping, and was said to be Turing complete, which basically meant that it could simulate a single tape Turing machine. Essentially, this was a basic computer. Now, Ada Lovelace built her algorithm to calculate Bernoulli numbers, and it was run on this device. So basically, she created a massive calculator. As such, this is widely considered to be the first complex program. But as you've seen, there was programming prior to Ada Lovelace. However, her algorithm was considered to be the first complex program, and thus she's been credited as being the world's first computer programmer. Now we have the late 1800s with Herman Hollerith starting his company called the Tabulating Machine Company. This later became IBM through various mergers and acquisitions. He again used punch cards, and his machine was developed for tracking sensors. So prior to his machine, everything was done by hand. It was very inefficient, and there obviously was a lot of error. Other uses for his machine was things like timekeeping for employees, scales, and automatic meat slices. So in the 1940s, we are into the electronic computer age, and this big machine you see in the slide is called Eniac. Now, Eniac is considered to be the first electronic computer. Eniac was developed to calculate artillery firing tables, And it is essentially just a collection of machines. They would call each machine a function table. And really, each of these machines was sort of sub-machines of each other. They were interconnected, so it kind of gave them a bit of complexity. But just like how we now would write a simple function, with Eniac, one of the sub-machines would perform just one simple function. What's interesting about Eniac is that it didn't use any kind of punch card programming or active programming that resembled opening and closing of valves. The function tables had about 1,210-way switches. Now these took weeks for the programmers to design, and then about a few days for them to actually set up the cables and connect the switches and make sure everything's in place. And then obviously, once you have everything set up, you've got to test your program. So this had to be run multiple times before they had to change it again. And now to debug Eniac was more of a physical process because you literally had to climb into the machine and reconnect cables, redo switches. I mean, it's really good that we're over that stage. Now, so yeah, we're in the electronic computing age, and here we're going to see something that most of us are actually very comfortable with and we're used to, and that's machine code and assembly languages. Machine code is basically just instructions that are directly executed by the computer's CPU, and nobody writes this anymore since it is very difficult firstly to write and then to try and understand. I mean, a fun fact is that the USA copyright offices will allow you to copyright computer programs and register computer programs. However, they will not copyright anything written in machine code because they cannot tell if it's original or not. And I found that very interesting. They actually say that trying to study or analyze machine code is vaguely similar to analyzing DNA molecules atom by atom. And that's why we have the birth of assembly languages. So assembly languages are very similar to machine code in a sense where they're very low level. The thing about assembly languages is that a language has to be devised for each computer architecture. So you can't just move one language from computer to computer. Right, then moving on to high-level programming. What it means to be high-level is abstraction from detail. And the more abstract you are from machine code, the more high-level you're said to be. So it is important to understand that high-level languages were mainly built for usability. So where machine code is written to be very optimal and have no problems, etc., high-level languages are basically just meant to be usable. In high-level, we have compilers and we have interpreters. So the interpreter interprets the syntax and then will execute in machine code, where the compiler will compile directly down to machine code. Sometimes the differentiation between the two, compiler and interpreter, gets a bit blurry, but that's the basic difference between them. From high level, we moved into programming paradigms. So programming paradigms is a way to describe programs using style. So the very first one we're going to talk about is procedural or imperative programming. This basically uses statements that change the program state and describes how the program would operate. So examples of that would be C#, C, COBOL. Then in 1952, Grace Hooper created a system or developed a system that could convert plain text into computer code. This would later become COBOL, which we use now for like data processing and, all right. Then we're moving on to declarative programming, which describes a problem rather than the solution. So like database programming, an example there is SQL. Then we have functional programming, which is not used very often now. It's somewhat declarative. They use pure functions to avoid the state changes, and the output is very much dependent on the input. Examples of this would be Hope and Haskell. And finally, something we're all very, very familiar with and comfortable with is object-oriented programming. The main objective here of object-oriented programming was based around objects. And then the object has fields which contain data, that is your attributes, and then the object has fields that contain code, which are your methods. And the key feature of object-oriented programming is that the method can access the data and modify it within the object. So examples of object-oriented programming languages are Java, JavaScript, Ruby, and C++. Moving on, in 1971, Bob Thomas created the world's first virus and called it the Creeper. And then in 1972, the first antivirus was created, or it was called the Reaper, and was said to be the antidote to the Creeper. And this was developed by Ray Tomlinson. So we've seen the progress through the centuries, and I'm pretty sure that everyone in the room is wondering where to from here. So just as the very first machines were the building blocks to what we know today, like OOP and all of the paradigms that I spoke about, those same paradigms and languages will be the foundation for something more advanced in the future. And for me, that would be artificial intelligence. So programmers can use AI techniques such as machine learning and deep learning to develop software for network security. As time goes on, the technology will evolve to such an advanced degree where AI will be the only realistic way to develop with the consecutive cybersecurity threats. AI will also reach our workforce. So that whole thing about AI being a job killer is just one side of the coin, because while 75 million jobs, yes, okay, they might disappear. At the same time, approximately 133 other million more expansive, more engaging, less repetitive roles will be created or will open up. So, I mean, at least we know we won't be completely replaced. As the machines develop, AI will become more integrated into our daily life, to a point where computer programmers and even us normal people will be able to control a lot of the aspects around us using artificial intelligence. Right, so this was a broad overview of the evolution of programming. I hope we all may have a better understanding of what makes computer languages different and where, like, you know, where we started from and where we're heading and where we are. As software developers, we are trained to, you know, pick up patterns and analyze patterns. And with everything discussed today, we can see that software will never stop improving. Therefore, we know that although artificial intelligence may be our future, it is only the beginning, or rather it's just the birth of something more expansive and infinite to come. And we can all agree that the cycle will never end. Thank you.
Thank you, Sandy. The floor is now open for questions. Feel free to ask them in the chat. Right, I don't see any questions coming in.
Likewise.
All right, so this concludes our Takeaway Talk for today. Thank you everyone for joining, and we'll be back next week.
Thank you, peoples.
Oh wait, we've got one question. Do you think the metaverse will become a thing, or is it the last roll of the dice?
Definitely will become a thing. Like I said already, the AI is just the beginning. The metaverse is obviously just starting up, and once it takes full swing, That's pretty much our future. I mean, I believe personally.